Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 21, practice session 3, in which we will solve our next problem, number 22, which is based on a tradition of alternative reasoning in general, and more specifically, alternative reasoning with inversive geometry in particular. In any hard science, be it mathematics, theoretical physics, or computer science, the so-called alternative reasoning works the same way as follows. Let us say we model a given well-defined academic problem with a point, which we will call P4 problem, and let us assume that this well-defined academic problem has a known solution or a known answer. Let's put it this way. We will model this answer with the point A for answer. And such a problem usually has a traditional or intended solution, which we will depict with a zigzaggy line that meanders somehow from the initial point, which is the problem, to the terminal point, which is the answer. But the so-called alternative reasoning should be an integral part of the very fabric of studying and learning mathematics, theoretical physics, and computer science, precisely because we achieve at least two goals when we engage in the alternative reasoning. This is how we learn the subject matter, and this is how we move the proverbial needle in that particular branch of hard science, mathematics, theoretical physics, or computer science. Now, the situation here is the following. When we know that one solution of the problem already exists, it is quite uncomfortable and quite challenging to even overcome the psychological resistance in order to start looking for a new solution. In other words, many times students ask the following question: well, we already know an existing solution. Why should we look for yet another one? Well, the answer to that question is precisely that. This is how we learn the subject matter, and this is how we move the proverbial needle. What does that mean? Well, on the one hand, when we look for an alternative solution that may go, for example, this way or that way, and then terminate at the answer, or it can go this way, meander somehow through some interesting material, come this way, and yet another solution may also unfold in some other interesting way. We juggle different layers of, let's say, mathematics, and the very act of juggling this seemingly different layers of mathematics is precisely how we learn mathematics in general, or in any one specific vaguely defined layer of mathematics, be it real analysis, complex analysis, geometry, theory of graphs, theory of numbers, and so on. The point number two is the following. The end goal of your, let's say, mathematical education is to move the proverbial, let's say, mathematical needle and create a knowledge that did not exist prior. And what does that mean? That means that at some point in your travels, if you dig long enough, you will come to a thin blue line, which will say, this is the end. This line right here is the end of the existing textbook knowledge. And the burden of moving the proverbial mathematical needle or creating a new unit of mathematical knowledge will be precisely on you. And how do you do that? Well, at that point, you will be facing an open-ended task that is psychologically uncomfortable for many people. And in order to do that, in order to create the next unit of textbook knowledge, it pays to engage in the so-called dress rehearsal and try to gain and obtain a mental habit of always looking for alternative ways or alternative means to solve a given problem and obtain the answer for that problem in some different way that may not be the intended way. And that is why we do that. That is why it pays to practice over and over and over again to come up with an alternative reasoning for a given problem and obtain evidently the same answer. And in this practice session, we will do just that. We will practice the art and craft of alternative reasoning based on a problem that is motivated by the so-called angle optimization problem of Regiomontanus. The original problem of angle optimization of Regiomontanus was named so after the German-born gentleman who went by the name Johann Müller. He lived between the years of 1436 and 1476, apparently for only 40 years. He was born in the vicinity of the German town Königsberg. Apparently in German, Königsberg is a compound or a composite word that means two things. Königs, that means of royal descent, let's say, and Berg, that means a mountain. And my take that Mr. Muller here was quite flamboyant. He had an exaggerated opinion of himself and of his intellectual abilities. Apparently, modesty was not one of his virtues, and the way the tradition went back then, he named himself in Latin, and in Latin his name Regiomontanus is also, or Regiomontanus also is a compound or a composite word that consists of two words, regio, which means, let's say, of royal descent, and montanus is mountain. So there you go, royal mountain in Latin or royal mountain in German. And we now know, we have the documental evidence that in his correspondence with the contemporaries of his time, he shared with his friends the problem that now carries his name, the problem of angle optimization of Regiomontanus, and that problem went as follows. The objective in this problem is to find the point x on the floor that is that many units of distance away from a wall. If you are located in a museum and you want to view a picture that is hanging on the wall that is perpendicular to the floor as shown over here, and it is known, let's say, it doesn't have to be that way, but let's say the very bottom of this painting is a units of length above the floor, and the top of the painting is b units of distance away from the floor. And the question here is, how do you find the point x from which this particular painting, the size of b minus a, is viewed under an angle theta that is maximal. As of the year 2026, the year in which this episode was made, the corresponding wiki page for the angle optimization problem of Regiomontanus lists three distinct solutions. The solution of this problem that is based on differential calculus, the solution of this problem that is based on high school algebra, and the solution of this problem that is based on elementary synthetic geometry. For example, the solution of this problem that is based on high school algebra hinges on the following mathematical fact. Arithmetic mean of two real numbers is never smaller than the corresponding geometric mean. And the two entities equal one another. The equal sign here holds if and only if these two entities that make up these two magnitudes, arithmetic mean and geometric mean, equal one another. In other words, the equality sign is achieved only if and only if x is equal to y. Now, of course, the first two solutions of the angle optimization problem of Regiomontanus shown over here, the differential calculus-based solution and the high school algebra-based solution. They are analytic in nature. They, of course, produce the correct answer to this problem shown on the bottom left of your screen over here. The distance, the mystery or the sought after distance from the point on the floor to the foot of the painting, this distance right here, is equal to precisely geometric mean of these two distances from the bottom of the painting to the floor and to the top of the painting to the floor. This answer is, of course, produced by these two lines of reasoning, but despite the fact that these two, let's say, analytic approaches produce an analytically expressed answer shown over here, these two solutions do not really paint any geometric picture of that solution. In contrast, the solution of the angle optimization problem of Regiomontanus that is based on elementary synthetic geometry does paint a quite visual picture of the solution of this problem, and it turns out that the point x in this case can be obtained with Euclidean tools alone, because that point x is the point that is none other than the point of tangency of a circle that passes precisely through the top of the painting, the bottom of the painting, and touches the floor at this specific point. And if we go back to the theory of circles, then in the theory of circles there exists a wonderful theorem that Euclid, for example, proves in his Elements, book number 3, proposition 36. Book number 3, proposition 36, you can look it up online. And according to that theorem, the square of the tangent, the square of this tangent right here, this distance, in other words, x squared, is equal to the rectangle on the second. In other words, if we take our floor and model it with a straight line, then we take our painting as a line segment of non-zero length and we extend the straight line through the points that delineate this painting all the way in this direction towards the floor, then the corresponding two straight lines will intersect. And this point right here, let's call it the point C, will play the role of a point where two geometric objects meet or intersect. A tangent to a circle through this point and a secant to the same circle through the same point. And this is what the essence of book 3, proposition 36. In this case, this is the algebraic expression that captures the synthetic geometry heart and soul of this theorem. The square of the length of the tangent is equal to the product of the outer segment of the secant to that circle and the entire segment of that secant. But in our case, the true power or the true value of this theorem comes from the fact that this theorem holds for any secant. If we construct any other secant for that circle, then that very same proposition or the very same theorem will hold. And that means that the angle that is formed by the line segment, let's say, or a straight line that passes through the given 2 points, and a straight line, which we can designate with L, that angle can actually be any reasonable angle. It doesn't have to be right. And that means that if we, for example, take our line segment, this line segment right here, let's say we'll call it A, B, and we will rotate that line segment about the point C in the parent plane this way or that way, then the location of the point X will not change, and it will remain one and the same, precisely due to the wonderful theorem from the theory of circles. And in order to demonstrate this fact, I've put together this time not an animation, but a visual demonstration of the fact. In this demonstration that you will see in a few seconds ago, I put it together with a free software called GeoGebra, and I needed a point that sits on the line segment AB in order to move it around. And you will see that I have actually two, as you might expect, two solution circles that pass through two given points and touch a straight line L. You will see that point. I will move this point around, and as I move that point around, pay attention to the fact that while the sizes of the corresponding circles that pass through two given points and touch the given straight line, they will vary. One will decrease, the other one will increase, and so on. The location of the tangency points, the locations of the tangency points remain fixed at all times. Now that you understand why the angle between the proverbial painting, the line segment AB, and the proverbial floor or the straight line L in the original angle optimization problem of Regiomontanus does not matter, and that angle can be any reasonable one, we arrive at the so-called generalized angle optimization problem of Regiomontanus, in which we're given one fixed straight line L, and we're given one fixed coplanar with the straight line L, line segment AB. And the question in this generalized problem is the following: what is the point, or what are the points from each of which the given line segment AB is seen under an angle that is maximal? And in this generalized version, this particular problem of optimizing a particular geometric magnitude can play the role of a model for a number of very different real-life applications. For example, let's say in your house you have a slanted roof or a slanted ceiling, and in such a situation you cut a skylight, or basically you installed another window in your roof. You cut a hole, you put the window and everything, and now the question is, where on the floor under that skylight do you find a spot from which the skylight is seen under the angle that is maximal? Because in this particular spot, for example, you can put a table in order to ensure the maximal amount of sunlight, for example, or if you like to read books, where do you put a chair so you have the most light falling on your book, and so on. Yet in another case, let's say in your town you have two streets that run under an angle like so, and over here you have a building whose facade has quite an exciting amount of architectural details that you like to use. So the question is, on the side street over here, where is the point from which you can inhale, so to speak, the facade of this building, which has interesting details for you, in such a way that the angle from which you view that particular building or the facade of the building is maximal. Yet in another case, let's say if you play soccer, then the soccer field looks like this. We have the situation going like this. We have a couple goals over here and a goal over here. This is the middle, circle, circle. So the question is, let's say you run along the side of the soccer field. So the question now is from which point on the side of the soccer field or in its close proximity, it doesn't have to be rocket science, but basically fundamentally from the side line of that soccer field, what is the point from which the goal of the opponent is seen under the maximal angle, and that gives you perhaps the best opportunity to score, to take a shot and score if you see an opportune moment, for example, and so on. Think on your own where you can apply this generalized angle optimization problem of Regiomontanus in the practical setting on your own. But the problem number 22 will not be this generalized angle optimization problem of Regiomontanus, but it's very much more narrower focused setting. And before we construct the statement of the problem 22, we need to cover some number of details. The first detail is the following. We already know that even in the generalized case, the angle optimization problem will have or may have either a unique solution or it may have two distinct solutions, because the candidate points from which the given line segment is seen under the maximal angle are generated by two circles, each of which is tangent to the given straight line and passes precisely through the extremities or the points that delineate the given line segments. The given line segment then across these two candidate solution circles, the solution circle S1 or the candidate solution circle S1 and the candidate solution circle S2, we are actually to choose the one that generates the larger angle between the two. And in the end of this episode, just in case, we will show that if the radii of the candidate solution circles are distinct, then necessarily one is larger, the other one is smaller. And in this case, we are to pick the smallest circle because the smallest circle will generate the tangency point x that will guarantee or that will ensure the maximal angle. And in that case, the solution of this generalized angle optimization problem is unique. But if it so happens that the candidate circles S1 and S2 have exactly the same radii, then the solution of the angle optimization problem, the generalized version after the problem of Regiomontanus, will have two distinct solutions, each of which is generated by corresponding circles. So now the question is, how do we construct physically? In many textbooks, you will see just construct these two circles, generate a proof, the solution is done, and we move on. But now we slow down a lot. We want to construct a very highly focused and very tactical problem. How specifically in practice, let's say, do we recover the locations of the points x and y, and how do we construct these two candidate solution circles, the candidate solution circle S1 and the candidate solution circle S2, using nothing but the Euclidean tools, a compass and a straight edge alone. It turns out that in this formulation, the generalized angle optimization problem of Regiomontanus can be reduced to the so-called LPP, or the second problem of Apollonius or Apollonius problem. And we actually enumerated these Apollonius problems in there are 10 such problems altogether, and we discussed these problems in the seminar where we dealt with three-circle problem of Apollonius. LPP, if you remember, stands for line, point, point, and that is precisely one of the problems of Apollonius, numbered S2. How do we construct a circle or a set of circles, each of which passes through two given points, A and B, and is tangent to a given straight line? All the objects are fixed and coplanar. And before we jump into the construction of the statement of the problem 22, we need to address one small detail, and that detail comes down to the mutual juxtaposition of the line segment AB and the given straight line L. If you think about this problem even for a short while, then you will quickly realize that in this case there exists only two angular mutual juxtapositions of the input objects, and these two angular mutual juxtapositions amount to the following. Either the straight line L and the straight line through the points A and B are parallel, or they are not parallel. In the first case, when the straight line L and the straight line through the points A and B are parallel, then the answer to this generalized angle optimization problem of Regiomontanus is trivial. The mystery point X is located on the straight line L in such a way that the triangle AXB is isosceles, which means that in order to locate the mystery point X on the straight line L, all we have to do is construct the perpendicular bisector of the line segment AB, and where that perpendicular bisector intersects the given straight line L, precisely that point marks the spot, and you should be able to generate a proof of this statement on your own. As a hint, the way I would do it is the following. I would construct a circle that passes through the points A, B, X, then I will pick any other candidate point P on L, and then use the angle between the seconds for the circle. In this case, you will see that the angular measure in this case between these 2 seconds will be what? Half angular measure of this arc minus half angular measure of this arc. And you will come down, you will realize that as long as this arc over here is not zero, we always subtract from, so the angle in this case is always less than, but over here evidently the angle is maximized. I will not dwell on this. In the second case, when the given straight line L and the straight line through the points A and B are not parallel, we have 3 mutual juxtapositions that cover all the possible cases. In the first case, the straight line L intersects the given line segment AB at a point, we'll call it O, that is strictly interior to the line segment AB. In other words, the straight line AB and the straight line L intersect over a point O such that the point O is located strictly in between the points A and B. In this case, it is evident that the mystery point X is precisely the point where these two objects intersect. That can be seen that if we, with the following experiment, we grab any point, then this angle right here is the angle under which the line segment is seen. So as we approach point X from, if we approach the point O from this side, or we approach the point O from that side, it doesn't really matter. The angles become larger and larger, and in the limiting case, when the point X coincides with the point O, then the angle theta will be precisely equal to pi radians, or 180 degrees, and under the circumstances that will be the maximal angle. Not interesting. In the second case, we have the given straight line L passing through either one of the extremities or through either one of the points that delineate the given line segment, through the point A or through the point B. In this case, also with a straightforward and very short analysis, it can be shown that depending on the side from which the candidate point X approaches the given point that these two objects have in common, this angle will be different. From this side it will be one angle, from the other side it will be the other. The same logic applies in this case, and that means precisely that in this case the angle under which the line segment AB, the maximal angle from which the given line segment AB is seen from the straight line L, is not defined. Not interesting, we throw out. So far we throw all the material that you see from this point onward to the left, we throw out. We're not interested. We're now only interested in this third case, when the given straight line and the given line segment AB are positioned with respect to each other in such a way that none of these cases apply. It means that the line segment AB is not parallel to the straight line L, and these two objects have precisely 0 points in common. Now that we have all the context that we need, we can put together the statement of the problem number 22, which is solve the LPP, line point point problem, or the second problem of Apollonius using inversive geometry and assuming that the input objects are in their most general position shown over here. We discussed this general position in the previous segment. We understand what that means, and we are to use Euclidean tools only. Euclidean tools only, and that means that we are to use only a compass and a straight edge. And before you deep dive into the solution of this problem, I want to make sure that all the members in the audience understand what the objective of this problem is. The objective of this problem is not to find a simplest, the most elementary, the cleverest, the most elegant solution or the shortest solution possible. No, the objective of this problem is to precisely and specifically use the machinery of inversive geometry in order to construct the two candidate solution circles to the generalized angle optimization problem of Regiomontanus, because precisely by doing so, we will be practicing applying the newly learned material to the process of solving technical problems. As such, in order to make sure that you do not waste your time, here is a short survey of solutions of the problem that is close to the problem 22. That is not the intended solution of this problem as it is formulated. In order to make sure that all our viewers get this out of their system right away before they take on the problem number 22 in its intended form, the very first brute force idea that comes to mind when we take on a similar problem is the following. Simply construct the geometric mean of two line segments and game is over. I will not be delving into the gory details of why this construction works. You were expected to study this in your middle school Euclidean geometry curriculum, but the idea here is the following. We glue the line segment of length B to the line segment of length A, glue these two line segments together, then we bisect them with the perpendicular bisector in such a way that this distance is equal to this distance. This bisector will give us the point O. This point plays the role of the center of the circle that has this radius. We simply construct this circle right here, and then this straight line through the point where the two line segments are adjoined will cut precisely this line segment right here will be the square root of A times B. This is easy to prove. Again, I will not be spending time on this proof. You're expected to know all this in your sleep. And that, by the way, construction tells us that if one of the line segments AOB is of length 1, then we know how to construct geometrically, how to construct the geometric equivalent of a square root of any, in this case, let's say, positive real number. So once you know how these things work, in our case, we take the general position of the input objects. Let's say this is our straight line L. This is our line segment. This is the point B. This is the point A. We already agreed that if we construct the straight line that runs through the points A and B extended, the straight lines A, B, and L will intersect. Let's say we will call that point, let's say we'll call that point C. Then all we have to do is construct a perpendicular to the straight line L through the point C, perpendicular. And let's say on that perpendicular, we measure this distance over here. Let's say if this distance is A and this distance right here is B, then we measure distance A. This is A right here. And we measure this distance as B right here. This distance is B. So AB, we cut this guy in half, and using this point that we obtain as the center, we construct a helper circle that passes through these points, and the 2 points where that circle intersects the straight line L are the candidate points. Game over. So we, let's say, bisect this line segment with the perpendicular bisector of AB. That's one circle, and if we have this, then we bisect this line segment that will somehow intersect this guy. Let's say, pretend that this is it, and this will be the center, and this will be another circle that will touch the given line, the given straight line L, and pass through the points A and B. This is a very straightforward construction, but again, one more time, in order to make sure that you get this out of your system, this is not the intended solution of the problem 22. If you joined after season 2, I recommend that you watch season 1 episode 3 through season 1 episode 7. This is where we study in a dedicated manner the so-called transform and conquer problem solving approach, because all the other solutions of this problem are based basically on this this or that form of transform and conquer problem solving approach. In this case, we execute the following maneuver. Let's say we're given the straight line L, and we're given our line segment AB in its general position. Then we see that, let's say, in the interesting case, we can construct the perpendicular bisector of that straight line, of the line segment AB, and we know that that perpendicular bisector will carry the centers of the two candidate solution circles. In other words, if the solution circles for this problem exist, then they will sit on that perpendicular bisector. As such, we pick any one. It doesn't really matter. See, this is the beginning of the transformation. First, we solve a transformed problem, and then we find a way to solve the original problem. That is, pick any point on this perpendicular bisector, it doesn't really matter, and then draw a circle that is centered at that point. Let's pretend that we pick this point over here. It doesn't really matter. Now we extend this straight line AB until it intersects the given straight line at the point C. And what is the solution of the transform problem? Well, we choose this circle arbitrarily, but through this circle, to the circle, we can construct the tangent straight line through the point C. Why would we do that? Well, we would do that because the straight line L is fixed, the points A and B are fixed, the objects that make up this second are fixed, and remember book 3 proposition 36, x squared is equal to A times B. Constant, their product is a constant. That means the length of the tangent, let's say tau squared, is equal to A times B. That means that the length of tau is one and the same regardless, remember, of the angle that this tangent forms with the second. That means that the locus of all these points, this tangent right here, this tangent tau, the length of this tangent, or let's say x, it will be fixed in one and the same. And what do we call the locus of points that are distant from a given fixed point C by the same amount? This is a circle, so the orbit, or the trajectory, if you will, of all such points is precisely the circle that has the point C as the center, and that magnitude, that length, as its radius. So if we construct that circle, it will intersect our straight line at 2 points again, the second point over here, and once we have this point over here, for example, let's say connected with B, bisect the point where this bisector and this bisector intersect, gives us the center of one solution circle that passes through points A and B and is tangent to the straight line L right here. And somewhere here will be another point, very large circle, but we understand how to construct it. Connect, let's say, points A and B, perpendicular bisector where these two bisectors intersect. marks the spot of the center of the second candidate solution circle that is tangent to the given straight line L and passes through the points A and B. But again, this is not the intended solution of the problem 22. Yet another solution of the problem like 22 that is not the intended solution of the problem 22 it is as it is formulated is a solution that is based on the geometric transformation of homothety or uniform expansion or contraction of a plane with respect to a point by a certain coefficient. In this case, we work the other way around. If we're given the straight line L, our line segment AB in the general position, we construct the perpendicular bisector of the line segment AB. That perpendicular bisector, if it intersects the straight line L, which, as we said, it should, so then this intersection will take place over the point C. Here we solve the transform problem as follows. We already construct an arbitrary helper circle that touches the straight line L at any arbitrary point. That much can be given because we don't care about the constraints that this helper circle must pass through the points A and B. Pick any point, construct a perpendicular. Pick any point, such as the point T, on the given straight line L. Construct a perpendicular, lowercase p t, to the straight line L through the point T. That perpendicular will intersect the bisector of the line segment AB in this point over here. Snap a circle, and that circle already carries all the needed information in it, all the information that is tactically useful for us already baked into that circle, and the mutual juxtaposition of the input objects. That is, through the point A, we draw a straight line through the point C. That straight line will intersect the helper circle at 2 points, M and N. And in some sense, the point M is the image of the point A, and the other way around under the homothety of the plane with respect to the center C. If we uniformly expand the parent plane, in other words, we pump air into the helper circle until staying tangent, it starts growing, 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 and boom, it passes precisely through the points A and B. So how do we locate the tangency point? Well, draw a straight line MT like this, and then draw a straight line, let's say lambda 1, that is parallel to MT, like this. Let's pretend that this is a straight line parallel, lambda 1. Well, where that straight line intersects L, this will be in some sense the image of the point T. I probably messed up it badly visually, but you get the point. This point right here will be the image of the point T. And once we have it, again, bisector, boom, the point, and voila, this is our circle. And how do we recover the second candidate tangency point? Well, we draw the straight line, construct a straight line lambda 2 that is parallel to the line segment MT. This is the second one, see? So we draw the straight line or the line segment MT, and then through A, this is through A, and this is through A as well, like this, parallel like this, and this will be the second point. So here will be our point number 1, here will be the point number 2. We have our two circles that somehow pass through these 2 points and tangent to the straight line L, and then across these 2 circles we pick the smaller one, because the smaller one will generate the larger angle under which the input line segment is seen. But again, this is not the intended solution of the problem 22 as it is stated. And now on to an intended solution of the problem 22 as it is stated, and in some sense this is precisely how things will work in college for you if you get to go to college, where you'll be given some amount of theoretical material and then you'll be given a number of problems, in each of which you you will be expected to precisely apply the newly learned material and show that you can incorporate that new theoretical knowledge into a practical skill of solving a given problem. Again, the problem will be, it is expected that you will solve this particular problem not in any which way you can, but precisely and specifically using the theoretical material that you were given. And in our case, how can we bring in the machinery of inversive geometry in order to solve the problem 22 as it is stated? Well, we will use again fundamentally the transform and conquer problem solving approach. If you joined us after season 2, we recommend that you use my free season guides. These are the free PDF files that are available at any time. Pop that PDF file open in a separate tab in your browser. Scan for the names of the episodes, click on the links, watch the episodes, work your way through, understand how the transform and conquer problem solving approach works, then come back and you will be in a good shape. So here, the original or difficult to solve problem is the following. We need to construct two curved objects, two circles that satisfy the following two constraints. Each of these circles must be tangent to a given straight line, and it has to pass through two distinct points which are in their general position with respect to the given straight line. And precisely the reason for the problem to be rated as difficult is because the objects that we're required to construct are curved in some way, circles. They're difficult to deal with. So how do we gain a competitive advantage or a tactical advantage by using the transform and conquer problem solving approach? Well, in some sense, we already proved, I did not say these words during the lectures and during the seminars, but now we can say it. We actually proved so far through all the theorems that we proved. We proved that topologically, a circle and a straight line are equivalent. So straight lines and circles are topologically equivalent. It means that if we have a straight line, we can always replace it with the corresponding circle. And conversely, if we're given a circle, we can replace it with the corresponding straight line. So here, the basic idea of generating the intended solution for the problem 22 is the realization or the knowledge of the fact that instead of dealing with two difficult objects, two curved objects, we can replace two curved objects with uncurved object or straight lines. And constructing straight lines that are tangent to one circle is a task that we deem as much more easier or straightforward, or in some sense a previously solved problem. So how do we hone in on this idea and generate or synthesize actionable mathematics in this case? Well, the reasoning goes like this. Let's say we're given our straight line L, and then we're given two distinct points, A and B. However they are located doesn't really matter. B, A, this is our line segment, their general position. And we already seen through all sorts of solutions. The solutions, by the way, that I gave you the sample, the short survey of solutions of similar problem. It's not all-inclusive. There are other ways to construct, to solve the LPP problem or the second problem of Apollonius. I gave you just popular or characteristic ones, and we already know that we need to construct two circles that touch the straight line L and pass through the points A and B. Well, we already know that we proved a bunch of theorems which basically state the following, that if a circle passes through the center of inversion, then such a circle will be taken into a straight line, whether the power of inversion is positive or negative. The mutual juxtaposition of the circles and lines is not that important, but conceptually we know that we can flip any circle into a straight line. In our case, our target circles must pass. I need to draw this circle very large, and the other circle is somewhat smaller. Let's say like this. These two circles pass through 2 points A and B. So which point we pick, it is natural to pick one of these points as the center of inversion. Which one we pick, it doesn't really matter. For demonstration purposes, let's say I pick the point A. A is the center is the center of inversion, positive power. We do all the inversions only once. If we flip that circle, let's say we'll call it circle S2, this is the candidate circle S1, the candidate solution circles, and we have our straight line L. Remember that the circles S1 and S2, they touch. The circles S1, 2, they touch the straight line L. And we know that under inversion, the tangency points under the inversion, any inversion of the real plane with respect to a circle, whether the power of inversion is positive or negative, the tangency points are preserved. In this case, the straight line L does not pass through the center of inversion. And what does that mean? It means that the straight line L under the inversion, let's say with respect to a circle that has the point A as its center and the radius r, it doesn't really matter which one. You see, it's arbitrary. As long as it's greater than 0, we're good. I will not even bother drawing that circle. Well, let's say this is our circle of inversion, C. With respect to that circle, this straight line L will be taken into what? L will be taken into a circle. Remember, circle L prime that passes through what? Passes through the center of inversion. So L will be taken into a circle that passes through the center of inversion somehow. Well, let's draw it with the let's say with the green color. So this will be our circle L prime. So the straight line L will be taken into a circle, genuine circle that passes through the center of inversion, L prime. The circles S1 and S2, they intersect. They have a point B in this case in common. The center of inversion will be taken into the point at infinity. We know that A will be taken into the point at infinity, and conversely, the point at infinity will be taken into the point A. But the point B will be taken with respect to this circle into the point B prime. And what does that mean? Well, that means that if the original objects intersect at the point B, then their images intersect at the point B prime, at the image of the point B. But these circles, S1, S2, pass through the center of inversion. They will be taken, the circles S1, 2, they will be taken into the straight lines S prime 1, 2, such that S prime 1 intersects S prime 2 at the point B prime, where B prime is the image of the point B under the chosen inversion with the center at A. You see, B goes into, let's say, somewhere here, into B prime. Let's say this is B prime. And then the circles S1 and S2 will be taken into, of course, in my case, it looks completely unrealistic, but the idea here is that the circles S1 and S2 that touch the straight line L will be taken into straight lines that must touch the image of L, which is the straight line. So let's pretend somehow more realistically this, or let's do with green color, this will be the circle, the image of the circle S1, S prime 1, and this will be the image, of the circle 2, the straight line 2. So somewhere here they will intersect at the point B prime. And what is the point B prime? The point B prime is the image of the point B under the chosen inversion, centered at A with positive power. And this is precisely where we gain the competitive advantage sought after. Why is that? Because let's say we in the algorithm that we will put together in a few seconds, as a first step, what do? Well, first we will reflect the straight line L into a circle L prime that passes through the center of inversion, in this case the point A. Then in the chosen circle we will flip or reflect the point B into the point B prime. Now this is where we reap the harvest of tactical advantage of the transform and conquer. The problem of constructing straight lines tangent to the circle through the point B prime is already an easy, a problem that is rated as easy, or if you will, technically a previously solved problem. There are many ways to do it. It doesn't really matter. I will not go into details of how we do it, but fundamentally, this is a previously solved problem. So we construct two straight lines, each of which passes through the point B prime, the image of B under the chosen inversion, and is tangent to the image circle L prime, this and this. And once we have these straight lines, and that task again completely can be carried out as required with Euclidean tools alone, everything is nice. Once we have these two straight lines on the books, this is where we gain the competitive advantage. We go back to the recipe of transform and conquer, which tells us that at this point, once we solve the transform problem that preserves the technical essence of the original difficult to solve problem, we carry out the reverse transformation. Remember that in theory of groups, you will see this interesting thing. And once we do the reverse transformation, what will be the reverse transformation in this case? The reverse transformation in this case will be reflecting the straight lines s prime 1 and s prime 2 in the chosen circle with positive power 1s. Precisely these straight lines will be reflected into our candidate solutions. In other words, the other way around, our straight lines s prime 1, 2 will be taken, in this case, into the candidate solution circles S1 and S2. Now that you understand that, once we have these circles obtained, it will be one circle and the other. We can, first of all, already put an algorithm. We understand how we derived a competitive advantage and how we solve this problem using precisely the machinery of inversive geometry. Remember, the bits or units of theoretical knowledge that you're expected to possess at this point is what? Any circle that passes through the center of inversion is taken into a straight line. A straight line that does not pass through the center of inversion is taken into a circle that passes through the center of inversion. If two cooperating curves intersect, then their images intersect. If two cooperating curves touch, then under the inversion their images will touch, and so on. All this information comes, all this theoretical information comes together into this solution. And once we have these circles, we can already recover the points, the y and the x, that are the candidate points for the solution of our original generalized angle optimization problem of Regiomontanus. Once you solve the problem in general, and I want to emphasize one more time that the whole point of going through seminars and practice sessions that we do in this course is for you to be able to generate these lines of reasoning that I just presented a few seconds ago in the previous segment on your own. On your own, you're supposed to be able to discover the hidden potential of the solution or the hidden potential of applying inversive geometry to the process of solving the problem. Now, once we understand how we solve this problem in general, we can write up a nice sequence of steps to which we refer as an algorithm. And in this case, an algorithm that solves the problem 22 as it is stated in its intended form is the following. Step number one, we pick, let's say, the point A is the center of inversion, any radius of inversion whatsoever. Of course, for practical purposes, we want to pick the radius that is large enough so we can work conveniently with the material that follows. And that will be the circle of inversion. The power of inversion is positive, plus r squared. The power of inversion is positive. After that, we carry out the following two crucial steps. First, we reflect the given straight line into a circle that will pass through the center of inversion, and we reflect the point B, the other point that is not the center of inversion, the other extremity. We reflect it into its image. Of course, you understand that if you were to pick the point B as the center of inversion, you will reflect the point A in this step. And once this is done, you have your circle L prime that passes in this case through the center of inversion, the point A, and you have your image point B prime. Again, At the end of the next segment, I will discuss the situations when the point B prime happens to be inside the circle L. Of course, you will understand that there are no solutions to this problem. We cannot construct the tangent straight lines to a circle when the point lies inside the circle. So the point B prime can be inside the circle L prime, on the circle L prime, or outside. And we will discuss this, but this is minor details. So once we have these two objects, a circle and a point B prime, hopefully, again, hopefully located outside of it, it doesn't have to be, but in general, this is the interesting case when it does. Then we carry out the step number 4. This is where we win. Using Euclidean tools alone, we construct two straight lines, S prime 1 and S prime 2, each of which passes through the point B prime and is tangent to the circle L prime. Tangent to the circle L prime and passes through the point B prime. Once we do that, this is where we win. We go back to inversive geometry, and in the step number 5, we reflect the straight lines, the tangents S prime 1, 2, into the candidate solution circles S1 and S2 in the chosen circle with positive power 1, so everything is nice. Here, what follows next, in my free PDF chapter, the link to this chapter in my book, Inversive Geometry for All, you will see that I take the certain middle school steps in order to specifically recover the points y and x. But here, it is not that important. If you took the problem this far, you know how to handle the rest. And here, your specific steps may fork a little. You can go in two separate directions. Let's say, as a side effect of constructing the tangents S prime 1 and S prime 2, you already know the tangency points over here between the images of this point. You know this point and you know this point. Well, then you simply reflect these points in the given circle, and voila, you have your points y and x instantly. This is a no-brainer, so to speak. But let's say you do not have these tangency points, you do not know these locations, even though you really should. As a side effect of your construction, the way you do it, this is actually quite straightforward. Straight line through point B prime and the center of this circle, cut this in half, draw another circle, and boom, these are your points. So as the step number 6, you will simply reflect these tangency points in a given circle, and they will be your candidate points y and candidate point x. If you do not, then you know that the centers of the circles sit on the bisector of the line segment AB, somewhere over here. So here you will, you can do the following maneuver. That straight line will intersect, let's say, your circle, circle S2, let's say, for demonstration purposes, over here, and you have your you have 3 points that belong to the circle line segment, perpendicular bisector. You have the point, let's say O2 is the center, and then the perpendicular to L through the center marks the spot. Same thing over here. You have your point that belongs to the circle S1. You have another point over here, straight line, perpendicular bisector. You have the point O1, and then the perpendicular through O1 to L. Somewhere here, of course, I have a goofy drawing, but this straight line will mark the spot. Perpendicular, perpendicular, and voila, you have 2 points, candidate points y and x. And the only thing that remains to be done is the analysis out of these 2 candidate solution circles, that generate the points x and y, which one we pick as the solution of the general angle optimization problem of Regiomontanus. And as a final touch, just in case, in order to bring this problem home, let's say we constructed our candidate circles, the circle S1 that has the radius R1 and the center at the point O1. We have constructed the candidate solution circle S2 with the radius R2. Let's say R1 is in some sort of relationship with R2. The center of the candidate solution circle S2 is the point O2. The candidate solution point x and the candidate solution point y mark. We know how to obtain them. All of this has been done. We know the practical side of it. We know how to obtain these points. The question is, which candidate solution circle generates the solution point that maximizes the angle under which the given line segment AB, shown in green, can be seen? Well, the answer here is the following. Let us compare the angles AXB and AYB. These angles, we know that by the corresponding theorem from the theory of circles, the angle that is not central, that has its vertex on the circle itself, is 1/2 of the corresponding central angle that subtends the same arc. So we have for the angle AXB, it's 1/2 of the central angle AO2B that is written over here, and for the magnitude of the angle AYB, we have it that is 1/2 of the magnitude of the corresponding central angle AO1B. And now all we have to do is compare the central angles, and whoever wins this race, the larger angle, will point to the circle that will generate the solution point x or y, as the case may be. In this particular case, I made it so that the circle S2 has a smaller radius. In other words, in this particular case, R1 is greater than R2, and that means that the point O is located closer to the line segment AB than the point O1. So the claim here is that the angle AO2B, the magnitude of the angle AO2B, is strictly larger than the magnitude of the angle AO1B, precisely because the point O is closer. Remember that the points O1 and O2 sit on the perpendicular bisector of the line segment AB, and the center of the circle S2 is closer to that line segment than the center O1 of the candidate solution circle S1. Consequently, X is the solution, and in this case, it's unique. In other words, if the radii of the candidate solution circles S1, 2 are distinct, then our problem admits only one solution, or a unique solution. And in this case, that solution corresponds to the point generated by the circle with the smaller radius. Now, if the radii of these two circles were the same, then we would have two distinct solutions. And obviously, if it so happens that the radius R1 of the circle S1 is smaller, then we take the corresponding point Y as the solution. And in general, you can make this claim over here as a, let's say, previously proved theory, but in the course of a verbal face-to-face real-time examination, your math professor can ask you to prove it. And how would you prove it? Well, let's say the 1/2 of the line segment AB over here is designated with H. This is H. And the distance from either center of the candidate solution circle to the line segment AB is correspondingly, let's say it is D1, and over here it's D2. So D1 in this case is greater than D2. D1 is greater than D2. Their reciprocals will change the sign. 1 over D1 is less than 1 over D2. When we multiply both sides by the same positive real number, H, we have this ratio. H over D1 is strictly less than H over D2. But this ratio corresponds, gives a middle school definition of the trigonometric function of tangent. Tangent of theta 1 is less than tangent of theta 2. So here we take half of angles, of course. Half, theta 1, theta 2. But on the corresponding interval between negative pi over 2 and pi over 2, we have what? The trigonometric function of tangent is continuous and is monotonically increasing. Consequently, if one value of the tangent is less than the other, that corresponds to the argument that is less than the argument of the function whose value is larger. So theta 1 is less than theta 2. Consequently, we take between two distinct circles, between the circles with distinct radii, we take the circle with the smaller radius, and this is it. And also, You again expect to analyze remember the image of the point B prime. If it's located outside of the circle L prime, we have two solutions. If it's on the circle, it's one solution, and if it's inside the circle, then there are no solutions. Again, this is not the emphasis of this practice session. The emphasis of this practice session is on your ability to splice the knowledge of the theoretical material of inversive geometry into the solution of this particular problem. And this is it for this practical session.